Welcome to today's lecture on the fascinating topic of endocrinology. In this comprehensive script, we will delve into the intricacies of the endocrine system, explore its anatomy and physiology, study the role of various hormones in thermoregulation, and discuss how external factors can disrupt this delicate balance. So, buckle up and get ready to embark on this educational journey. To understand the intricate workings of the endocrine system, let's first take a closer look at its anatomy and physiology. The endocrine system consists of various glands distributed throughout the body, including the pituitary gland, thyroid gland, adrenal glands, and pancreas, among others. These glands secrete hormones directly into the bloodstream, which then travel to target tissues and organs, where they elicit specific responses. The endocrine system regulates numerous processes, such as metabolism, growth and development, reproduction, and yes, even thermoregulation. Neuroendocrinology focuses on the interactions between the nervous system and the endocrine system. Specialized cells known as neuroendocrine cells bridge the gap between these two systems, secreting hormones into the bloodstream in response to neuronal signals. Neuroendocrinology plays a crucial role in maintaining body temperature. For instance, the hypothalamus acts as the command center for temperature regulation, integrating signals from temperature receptors throughout the body and initiating appropriate responses to maintain homeostasis. Homeostatic control mechanisms are fundamental for maintaining a stable internal environment, including body temperature. The hypothalamus plays a pivotal role in orchestrating these mechanisms by receiving temperature inputs and coordinating appropriate responses. One such mechanism is vasoconstriction, wherein blood vessels constrict to reduce blood flow to the skin, minimizing heat loss. Conversely, vasodilation occurs when blood vessels dilate to increase blood flow, facilitating heat dissipation during periods of increased body temperature. Thyroid hormones, particularly triiodothyronine, T3, and thyroxine, T4, play a significant role in regulating thermogenesis, the production of heat in the body. These hormones influence the metabolic rate, which directly affects heat production. Thyroid hormones enhance cellular respiration and energy expenditure, leading to increased heat generation. This effect is particularly crucial in cold environments, where maintaining body temperature becomes even more challenging. Catecholamines, such as epinephrine and norepinephrine, also contribute to heat production and thermoregulation. These hormones are released by the adrenal glands in response to stress or low body temperatures. Catecholamines have several effects, including the stimulation of glycogenolysis and lipolysis, which provide fuel for increased metabolic activity and heat production. Additionally, they promote vasoconstriction, redirecting blood flow to vital organs and conserving heat. Brown adipose tissue, BAT, is a specialized type of adipose tissue predominantly found in newborns and hibernating mammals, which is crucial for thermoregulation. BAT contains a high density of mitochondria and is rich in uncoupling protein 1, UCP1. UCP1 enables BAT to uncouple oxidative phosphorylation from ATP production, leading to the generation of heat, rather than adenosine triphosphate, ATP. When activated, BAT can significantly contribute to increased heat production and energy expenditure. The hypothalamus acts as the central regulator of body temperature. It receives inputs from temperature receptors throughout the body and integrates these signals to maintain homeostasis. The hypothalamus contains thermal-sensitive neurons that respond to small temperature changes, initiating appropriate responses to balance heat production and heat loss. This delicate balance is crucial to prevent overheating or excessive cooling. Fever is a physiological response characterized by an elevated body temperature above the normal range. It is often triggered by an immune response to infection or inflammation, orchestrated by certain pro-inflammatory cytokines. During fever, the hypothalamus undergoes a shift, resetting the body's temperature set point to a higher level. This leads to shivering, vasoconstriction, and increased metabolic activity, ultimately raising body temperature and aiding in fighting infections. The hypothalamic pituitary adrenal, HPA, axis is a crucial stress response pathway extensively involved in thermoregulation. Stressful situations trigger the release of corticotropin-releasing hormone, CRH, from the hypothalamus, stimulating the release of adrenocorticotropic hormone, ACTH, from the pituitary gland. ACT then stimulates the adrenal glands to secrete cortisol, a stress hormone that modulates various physiological processes, including thermoregulation. During stress, cortisol can influence body temperature through its effects on metabolism and immune function. Sex hormones, including estrogen, progesterone, and testosterone, also have a role in thermoregulation. These hormones fluctuate during menstrual cycles and can influence body temperature regulation. Estrogen, for example, can affect vasodilation and sweating, potentially contributing to differences in thermoregulatory responses between males and females. These hormonal changes during menopause can also impact thermoregulation and contribute to hot flashes. Endocrine disruptors are substances that interfere with the normal functioning of the endocrine system, including hormone signaling and response pathways. Exposure to endocrine disruptors can have detrimental effects on various physiological processes, including thermoregulation. Chemicals such as bisphenol A, BPA, and phthalates, found in plastics and certain consumer products, have been implicated in disrupting hormonal pathways involved in thermoregulation. These disruptions can lead to dysregulation of body temperature and related health issues. As individuals age, changes in the endocrine system and other physiological processes can impact thermoregulation. Elderly individuals may experience reduced thermoregulatory responsiveness, leading to increased vulnerability to extreme temperatures. Hormonal changes, decreased muscular activity, and altered blood vessels' response to temperature changes are among the factors contributing to age-related alterations in thermoregulation. It is crucial to understand these changes to provide appropriate care for the elderly population. In conclusion, the study of endocrinology provides us with incredible insights into how our bodies maintain thermal balance. The interplay between hormones, the nervous system, and external factors enables the finely tuned process of thermoregulation. From the control mechanisms orchestrated by the hypothalamus to the effects of various hormones on heat production, it is evident that the endocrine system plays a vital role in maintaining body temperature. Moreover, external factors such as endocrine disruptors and the aging process can significantly impact thermoregulation. As future medical professionals, it is vital to grasp the complexities of thermoregulation and its intricate relationship with the endocrine system. By understanding these mechanisms, we can provide optimal care to our patients and contribute to their overall well-being. Thank you for joining me on this informative journey through the fascinating world of endocrinology and its connection to thermoregulation.